Hello, thanks for joining me as we finish off this Unit 5 on chemical energetics. To finish off today, we are going to look at the concept of Hess's Law and enthalpy cycles, where our lesson objective is to understand and apply Hess's Law through enthalpy cycles and to calculate enthalpy changes through bond energies and vice versa. Our learning outcomes that we're going to address just below there. So we looked previously in this unit at this idea of enthalpy changes and how we can calculate these enthalpy changes through bond energies, where we're breaking bonds and making bonds, and depending on what those values are, we'll either have a negative or a positive value, and that will either be an exothermic or an endothermic reaction. We're going to finish off today with looking at this concept of enthalpy cycles, which are very useful things that we can use to get the enthalpy changes in reactions that we can't measure the enthalpy changes directly in. It is based on the law of conservation of energy. These conservation laws are things that we've seen quite a few times. Conservation of matter, conservation of energy is the same thing. You can't create or destroy energy, you just transfer it into different forms. And this is the first law of thermodynamics. So this law of conservation of energy, energy can't be created or destroyed. This Swiss-Russian fella called Germain Hess, a Swiss-Russian chemist, came up with a very useful application of this law of conservation of energy. He applied it to chemical reactions and enthalpy changes. And what Hess said, and what his law states, is that the total enthalpy change during a chemical reaction is the same whether the reaction is made in one step or multiple steps. And we can see that over here. So usually when we think of a chemical reaction, we think that we have A plus B and we form some sort of product C. And that's going to have some sort of delta H for that reaction. However, if we can't directly measure this delta H of this reaction, we can use this concept of conservation of energy and this law that old mate Hess came up with to work around that. So even though we might not be able to do this directly, we might know that A plus B can make two different things. Let's say D plus E. And from here we could react those to get to C. And what it's saying is that the energy to go this way would be the same as the energy to go that way. It's just doing it in multiple steps. And that's what we're stating over here. So we've got A going to B, but that would be the same enthalpy change as if we went to some sort of intermediate. If we went to one intermediate and then to B, these enthalpies would be the same as that enthalpy. Or if we had two intermediates, if we went to D, then E, then to B, these enthalpy changes would equal that enthalpy change. The enthalpy change of the system, whether we're going in one step, two step, how many steps, is always going to be the same. So even though we might not be able to measure one enthalpy change directly, we can use other ones and we can get those indirect enthalpy changes and work out the enthalpy of a reaction that way. So the total enthalpy change is independent of the root of the chemical reaction as long as the initial and final conditions are the same. Hess's law tells us that the enthalpy change for the direct route is the same as the indirect route, irrespective of how many steps. So going directly from A to B would be the direct route, A to C to B would be an indirect route, A to D to E to B would also be an indirect route. The enthalpy change for these direct route and these indirect routes will be the same because of this conservation of energy, this concept up here, pardon me. We can use this law to calculate enthalpy changes that cannot be found through calorimetry. So let's now look at some specific enthalpy cycles that are based on enthalpy changes of certain reactions that we saw in the previous video. We looked at our types of enthalpy change, where we got enthalpy change of the reaction, enthalpy change of combustion, enthalpy change of atomization. Let's look at how we can use some of these in our enthalpy cycles. So we can use the enthalpy change of formation to get the enthalpy change of a reaction, which would look like this. In a chemical reaction, you would have the reactants forming some sort of products. And that's going to have a delta H, that's going to have an enthalpy change for that reaction. Now the delta H of formation was talking about getting the elements and forming a compound or a species from the elements, and this will give a delta H of formation. So if we have our elements down here, we can have a delta H formation to form the chemicals and the reactants. We can also have a delta H of formation to form the chemicals in the products. Now, what you have to do in these situations, so say if we couldn't calculate that delta HR directly, but we do know these two delta H's, we can use Hess's law to work out what this delta HR is. Firstly, we need to identify the root and the indirect root. So in a chemical reaction, where we had that one going reactants to products, and that's going to have an enthalpy change for that reaction. We've also got the enthalpy changes of formation, where we've got the elements and we can form the species that are in the reactants and we can form the species that are in the products. Each of these are going to have a delta H, an enthalpy change of formation, depending on what elements they are and depending on what products and what reactants they are. So you've got to identify the direct root and the indirect root, which is just simply what they sound like. The direct route is the quickest way to get somewhere. The indirect route is the not quickest way to get there, just the way you use direct and indirect in your everyday vocab. So in this case, the direct route is going to be this one. So the direct route is the shortest way there. The indirect route are the two arrows that kind of add up to each other. So you follow the arrows around. So the indirect route is going to be like that way. You're going the indirect route, whereas over here you're going the direct way. So you've got to be able to follow the arrows. The indirect route can't be that way. That doesn't work because in this case, your arrow is going the opposite way of this arrow. The arrows just simply have to line up with one another. So the indirect route and the direct route is that one because it's the direct way to get there. The indirect route is following this arrow around like that. And then from here, it just becomes very simple algebra. So if this delta H2, if all the energy is conserved here, it means that the delta H2, the energy to go for the direct route, is going to be the same as the energy to go the indirect route. So the energy to go this way is going to be the same as the energy to go that way. So delta H2 is equal to delta H1 plus delta HR. Now again, this is all based on the idea of conservation of energy. And Hess's law applied that conservation of energy to chemical reactions. So that's why we can do this. That's why we can say that the energy going that way is the same for the energy to go that way. Now from here, if we know this delta H and this delta H, and we wanted to know this delta H, well now we've got a simple equation and we can use some very basic just algebra arithmetic to rearrange that. So if we've got delta H2 is equal to delta H1 plus delta HR, we can arrange that to get delta HR is equal to delta H2 minus delta H1. What have I got over here? So that can rearrange to get that. Delta HR is equal to delta H2 minus delta H1. A few things to note. Equations need to be balanced. I mean, that's nothing new. All equations, that should just be a general thing that we say all the time. All equations need to be balanced. It's pointless to have an unbalanced equation. And we need to take into account the number of moles of each reactant and product. Let's do an example to illustrate what I mean by that. Calculate the standard enthalpy change for the following reaction. We have 2 NaHCO3 going to Na2CO3 plus CO2 plus H2O. Enthalpy changes of formation are, so we've got the delta H plimsoll. Remember this plimsoll, if we go back to the previous video, means the standard conditions. So the delta H formation of this from its elements is that much energy. Delta H formation for that is that much energy, so on and so forth. If you want to pause, have a go and check your answer, you can do that now and you can check it now. First thing you want to do is to write the chemical equation. So what were we given? We were given 2 NaHCO3 solid. Decomposition reaction. We're forming Na2CO3 solid plus CO2 gas plus H2O liquid. Now we were given our delta H with the plimsoll, so these are the states of all of these at standard conditions. Okay, now what? Well, let's have a look at this one here. So we've got our reactants going to our products, and we know the delta H. We don't know the delta H star, that's what we've got to work out. But we've got all the delta H formations for forming these reactants and forming these products from the elements. So we've got to put each of these atoms that we find down in their elemental form down here. So what do we find? We need a sodium. So a sodium comes as sodium metal in its element. We have hydrogen. Hydrogen comes as diatomic hydrogen gas. Carbon. Carbon we find is just carbon in the graphite form, the allotrope of carbon, that is the graphite. We had a video on the different kinds of allotropes a few videos ago in the states of matter. And then we have our oxygen, which would be diatomic oxygen gas, like that. So we can have sodium, hydrogen, carbon, and oxygen all react to form that, like that. And we can have sodium, hydrogen, carbon, and oxygen to form these three things in different amounts. Okay, now we've got to look at the delta H formations that we're given. The energy needed to form our reactant, which was the sodium bicarbonate, NaHCO3, was this much energy. So I'm going to put that much energy on my enthalpy cycle just here. So going up this way, to make one of those, that delta H, am I still in the camera? I am still in the camera. Delta H plimsoll of formation to form sodium HCO3 is equal to minus 950.8 kilojoules per mole. When I said before that we need to take into account the number of moles of each reactant / product, this is where we're doing that. So it takes this much energy to form that from its elements, but we're forming two of these. So we've got to bear that in mind, that we're doing this delta H formation twice because we need 2 moles of that. Hopefully that makes sense to you. If that's the delta H formation for one of them, and we got 2 of them, we got to multiply it by 2. Then we have a look at the delta H formation for the things that we have in our products. We have a delta H formation for sodium carbonate, delta H formation for carbon dioxide, and a delta H formation for water. So let's go ahead and put all of these values on our cycle. I might use a different color because it might get a bit messy here. All right, so we have the delta H plimsoll of formation for the sodium carbonate. We're making 1 sodium carbonate. So we're going to have how much energy? Minus 1130.7. We're forming 1 carbon dioxide, so we're going to have the delta H plimsoll formation of carbon dioxide. And that's going to equal minus 393.5 kilojoules per mole of energy. Oh, I'm sorry, this is getting a bit messy, but we'll get through it. And then finally, we got the delta H formation to form 1 water from our reactants down here. Delta H of formation of O2 is equal to minus 285.8 kilojoules per mole. Beauty. Now, let us have a look at some balancing things, because I haven't quite got this balance yet now, do I? So I've got all my delta H formations on there, which is good. I've got a balanced equation up here, but we're just going to make sure that we have a balanced equation down there. We've got 2 sodiums over here, so we need 2 sodiums down there, and we've got 2 sodiums there, so that's all balanced there. 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, that's all good. 1 carbon, 2 carbons, so I need 2 there. We've got 1 2 carbons over here. Then I've got 2 oxygens going to 6 oxygens, so I need a 3 there, and then I've got 3, 4, 5, 6 oxygens there. Beauty. Now we can start identifying our direct and our indirect routes. So to find the direct route and the indirect route, we've got to look at the arrows that lead on to one another. The arrows that follow each other around are these 2 arrows, like that. That is going to be the indirect route. That is going to be the direct route. So you can see these arrows can't go the other way. They can't go around like that. They can't go around like that, because they're all going to be conflicting with the direction of the arrows here. The arrows have to match up in the direction. What now? We've got the direct and the indirect route. We now need to work out our simple equations with all our delta H's to get the delta H of the reaction. So looking back over here, why have I written O2 there? That should be H2O. That's really strange thing to do, because that's the delta H formation of that H2O, not O2. Ignore that O2 there, that's meant to say H2O. So we've essentially got our delta H1 over here. We've got our delta H2 over there. Well, that's not in the frame. Delta H2 over with all of this. So we can see that delta H2 is going to be equal to delta H1 plus delta HR. The direct root is equal to the indirect root. Now it's just a matter of rearranging for delta HR. If I get delta HR, that's going to be equal to delta H2 minus delta H1. Now you want to plug in all your values, which I'm going to do here. Coming back up, our delta H of the reaction is going to be equal to our delta H2, which is all of these over here. So it's minus 1130.7. It's that one plus the delta H formation for carbon dioxide minus 393.5 plus the delta H formation for water minus 285.8. That's going to give me an answer of, oh, I've done something very wrong here. Let's try that again. 393.5 minus 1810. Then we got to minus it from our delta H1, which is 2 times minus 950.8. 2 times minus 950.8. That's going to be minus 1901.6. Be very careful with all of your minus and your pluses. Make sure you don't get them lost across the way. But we do that and we should get an answer that is hopefully correct. Minus 1810 minus 1901.6 gives us an answer of 91.6 kilojoules per mole minus 1. That is the delta H of that reaction. If I go back to screen, we should get an answer of 91.6 kilojoules per mole. Yes, remember our delta H's always have signs on them. So, plus over there. So that's saying the delta H of this reaction up there is that value, and we can calculate that because we know all of these delta H's, and we can use conservation of energy and Hess's law to work that out. You beauty. Let's have a look at a few more. Enthalpy change of formation from the enthalpy changes of combustion. So this was using the enthalpy changes of formation to get the enthalpy change of reaction. We can get the enthalpy change of formation from the enthalpy changes of combustion. We use enthalpy change of combustion where we react with the oxygen to get the enthalpy change of formation. As always, we identify the direct route and the indirect route. So in this case, we can get the delta H of formation by getting the elements to that compound, by working out the combustion products. So each of these, when you react it with oxygen, that's the combustion reaction. We can work out the delta H of these, and then we can use that to get the delta H of formation here. Identify the direct and the indirect route. You got to see which of these arrows will kind of add on to each other. It'll be this one and that one. So that will be the indirect route. That will be the direct route. Then we could say that delta H1 is equal to delta HF plus delta H2, which we can then rearrange to get delta HF as the subject. Delta HF equals delta H1 minus delta H2. Very similar to the previous one, only the arrows are going the opposite way. So we've got to be very aware of which way the arrows are going to find the correct direct and the correct indirect route. Another application of this, enthalpy change of hydration of an anhydrous salt. Difficult to measure delta H when anhydrous salts are hydrated. Can use the standard enthalpy of solution, do in the exact same manner. So the anhydrous salt, the enthalpy change to make the hydrated salt can be difficult to get that value, but you can get that value by working out the delta H for the dilute aqueous solution of salt from the anhydrous salt and from the hydrated salt. And then you can identify the direct and the indirect routes to work out the equation you need to get the delta H of hydration. So the indirect route would be that arrow plus that arrow. So the indirect route would go around like that. The direct route would be that. Therefore, the direct route delta H1 is equal to delta H of hydration plus delta H2. Rearrange that to get delta H of hydration is equal to delta H1 minus delta H2. You beauty. Okay, average bond energies. We looked at the idea last time of bond energies and how we can calculate the bond energies when we're breaking the bonds and making the bonds to work out if we've got an exothermic or an endothermic reaction. And we had our super catchy acronym called BendoMex, which means that the bond breaking is an endothermic process, bond making is an exothermic process. BendoMex. Bond breaking is endothermic, bond making is exothermic. Look previously at how to determine delta H from given bond energies. Go revisit the previous video in this series if you missed that or want to recap that. But essentially, if the energy to break bonds is less than the energy to make bonds, we'll get an exothermic reaction. And that makes sense if you think about it. If the energy to break the bonds, if you're making more energy than you are using to break the bonds, then you will have energy left over that will be given off. So you'll have exothermic. Whereas the vice versa of that, if the energy to break the bonds is greater than the energy to make the bonds, so if you're using more energy to break the bonds than you are releasing when you make the bonds, you will end up with an endothermic reaction. You'll be taking in heat from the surroundings. Now, what we can do is we can show this on enthalpy profile diagrams. Don't get these confused with enthalpy cycles. Enthalpy cycles and enthalpy profile diagrams are two different things. You want to make sure you're well aware which is which. So the cycles was what we just did in the previous question. Let's have a look at an enthalpy diagram. So I've got a question here that says, draw the diagram for the reaction of 2 HBr going to H2 plus Br2, where we have a positive delta H. So the enthalpy profile diagrams that we looked at in the previous video had energy as the y-axis, energy going up like that, and we had the reaction profile, so the reaction pathway going across like that, reaction pathway and energy. I'm given a delta H that is positive. That means it is an endothermic reaction. That means that my products are going to be a higher energy than my reactants. My reactants in this case were given as HBr. So I've got 2 HBr there. My products is H2 plus Br2. They're my products. I might even write that on there just so we're well aware. Reactants here, products there. So what I'm doing in this chemical reaction is I'm first breaking the bonds. I've got 2 HBr molecules. I've got to put energy in. Bond breaking is an endothermic process. I've got to put energy in to break these bonds, and I end up with a high energy transition state where I've essentially broken the bonds of the reactant. So that's what we have up here. And what we have is we've got 2 H atoms and we've got 2 bromine atoms like that. So this is the energy to break the bonds. So energy to break the bonds. Then I've got my 4 atoms. I've got my H, and my Br, and my Br, and they form products. So the H's form, the Br's form, and that releases energy. So this is the energy that is released, energy to make, and that's released to the outside surroundings. Making is an exothermic process, energy to make. So in this case, if my energy to break is bigger than the energy release when making them, we have a positive delta H. So we can show these processes on our enthalpy profile diagrams just like that. One thing that we didn't discuss is the idea that we're talking about an average bond energy when we're talking about bond energies. So the bond energy is given the symbol E. For example, this is showing us the energy of a carbon-hydrogen bond is 413 kilojoules per mole. But not all bonds are the same. They are affected by other atoms in the molecule. For example, the bond, the OH bond. Where's my red pen? If I have an OH bond in a water molecule, the OH bond there is going to be slightly different to the OH bond that I will have in an ethanol molecule. That should be CH2, that should be CH3. So even though they're both an OH bond, they're slightly different because these other atoms that are attached to the molecule will affect them very slightly. So when we report our bond energies, they're reported as an average bond energy, just using an average of all the different kinds of the same bond in different molecules. Here's a question that we can use an enthalpy cycle to get the average bond energy. Calculate the average bond energy of the CH bond using the following information. So we're given a delta H of formation for methane. delta H of atomization for half hydrogen, delta H of atomization of carbon graphite. Pause now if you want to have a go yourself, and you can check it when you push resume, when we do it on the whiteboard right now. Right-yo. So, what have we given? We're given a delta H of formation of methane. So, I've got my methane here. I'm also given the delta H of atomization and the delta H of atomization for hydrogen and carbon. So I want to work out what the bond energy of the CH bond is. So I can break that bond to get a carbon and 4 hydrogen atoms, and that will tell me the delta H for this reaction. That's going to give me the delta H for the bond energy, essentially. So down here I've got the elements. I've got my carbon in the graphite, and I've got my hydrogen in the gaseous form like that. So I can form over here and I can form over here. Excellent. Let us work out what the direct route and what the indirect route is. So the indirect is going to be this one, the arrows follow around like that, and the direct route is going to be that one. So over here, I am given a delta H of formation of CH4. So my delta H of formation, Plimsoll formation of CH4 is equal to, what value was it? Minus 74.8 kilojoules per mole. That says kilojoules per mole. Excellent. I got to make sure this is balanced, so I got 2 down there. That's all balanced. Over here, we were given some values for the atomization. So I got a delta H of atomization for half hydrogen and delta H of atomization for carbon in the graphite form. So over here, this is where the delta H of atomization for the half hydrogen is. So I'm going from the hydrogen in the gaseous form to just hydrogen atoms. But I'm given a delta H Plimsoll of atomization for half hydrogen, which is essentially 1 hydrogen atom. That was given a value of plus 218 kilojoules per mole. But I've got 4 hydrogens. So if I'm given the value for half 1H2, which is essentially the value for 1H, but I got 4 H's that I'm atomizing, I've got to multiply all this value by 4 because of the mole ratio there. Remember that the mole ratio affects how many of the delta H's you will have. So you've got to multiply that. And then we have the delta H of atomization for the graphite, which is going to be delta H, the atomization for the carbon, which was a value of 716.7, positive 716.7 kilojoules per mole. Lovely jubbly. What now? So we've got delta H1, delta H2, delta H of the reaction. So I'm going to say that delta H1, I might go back to my black pen here. Oh no, actually our direct route is delta H2, isn't it? So delta H2 is equal to delta H1 plus my delta HR. Well, I want to put that in blue to be consistent. So I'm going to rearrange that to get the delta HR. Delta HR is equal to delta H2 minus delta H1. And now I can plug some values in. So my delta H2 over here is this one. So I've got 4 times 218, which equals 872. And I've got 716.7, add all them together. I get a value of 1588.7. So 1588.7. And then I'm going to minus it from the one value over here, minus 74.8. That's going to give me a delta H of the reaction equaling minus 74.8. 1663.5 kilojoules per mole. But if I look over here, the answer is not that. And we can understand that because we want to know the average bond energy of one CH bond. But in my reaction over here, this is breaking 4 CH bonds. This is CH4. 1, 2, 3, 4. So this is the energy to break 4 of them. If we want to get the energy to break just one of it, I'm going to divide that by 4. I divide that by 4. I get an answer of 415.9 kilojoules per mole. So that's something you have to be very conscientious of when you are doing these kinds of questions. You need to get just the average bond energy of one of the bonds, and depending how many bonds of that you have in the molecule, you will have to divide it by that number. All right, big lesson today. The last thing we've got to do. So this is using the delta H's to get the bond energies. You can do it the other way around. You can get the bond energies using the delta H's. So we looked at using enthalpy changes to calculate bond energies, can also do the opposite. We're going to do an example of a Haber process. Haber process is a very important chemical reaction that you're going to come across a lot. So we're going to drill it into you as much as we can. It's essentially just the chemical reaction to synthesize ammonia, which is super important because that can mean that we can mass produce all sorts of food on a large scale to support all the people on Earth. Or a lot of the people on Earth. I don't know if I should say all the people on Earth. But it looks like this. It's nitrogen gas plus hydrogen gas forming ammonia gas under these conditions. All right, let's finish off by showing how we can get the enthalpy changes from the bond energies. So in this case, we've got to show the delta H of the reaction is that value using the bond energies that we have here. As we always do, if you want to pause and have a go yourself, you can do that now and then check your answer when you push play. To start with, we want to write the equation out like we do, but we're going to write it out a little bit differently. We're going to show all the bonds that are present in the molecules. So I have N2, N triple bond N, and I'm reacting that with 3 lots of H2. So H, 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 H. I have the delta H of the reaction that I want to calculate, and I'm forming 3 NH3 molecules. So, I'm forming 2 NH3 molecules, more accurately. So 1 and 2. Lovely. So I can't get the delta HR here, but I do know the energies. So what I can do is I can calculate the energy to break all of these bonds to form the atoms in just their atoms, just to make the atoms by themselves. So if I broke all these bonds, I would have 2 nitrogen atoms and I would have 6 hydrogen atoms. And then I can get the energy released when we make the bonds, and I can use my direct and my indirect routes to get the delta H of the reaction. So follow the arrows around. In this case, these 2 arrows lead onto each other, so that's the indirect, this is the direct. Let's pump some values in. So the energy I need to break the N triple bond N, that was given to me in the question, that was 945 kilojoules per mole. I'm not going to write units just to save some time. So I've got to break that, but then I've got to break 3 HH bonds. So the energy for 1 HH bond is equal to 436, but I want to break 3 of them. So I've got to multiply that by 3 because I'm breaking 1, 2, 3. Then over here, the energy of a NH bond was given to me. That's 391, but I'm not breaking the bond this time. Instead, this time I'm making the bond. So the energy is going to be released. So the energy is going to be the negative value, not the positive value over here. So the energy released when making an NH bond is equal to minus the energy taken of the NH bond because the energy is being released. So minus 391. However, I'm making 1, 2, 3, 4, 5, 6 of these NH bonds, so I've got to multiply that by 6. Then we can use our indirect and direct routes to get our maths equation. So delta H of the reaction is going to be equal to the delta H1. I'm going to say that's delta H1 plus delta H2. Delta H1, we're given values of, old mate calculator, 945 plus 3 times 436 gives me a value of 2253. 2253. And then I'm plussing that to the energy given off over here, which is 391 times 6, 2, 3, 4, 6. And then if I go 2253 plus minus 2346. I get an answer of minus 93 kilojoules per mole for my delta H. That is equal to minus 93 kilojoules per mole of energy released. And with that, that's the correct answer there. With that, we have finished this lesson and subsequently finished the unit on chemical energetics. What have we looked at? We have applied Hess's law to construct simple energy cycles and carry out calculations involving such cycles and relevant energy terms, with particular reference to determining enthalpy changes that cannot be found by direct experiment and average bond energies. And we've constructed and interpreted a reaction pathway diagram in terms of the enthalpy change of the reaction and the activation energy, as we always have. If you want to do some consolidation, here are some tasks. You can pause the video, start at the bottom, and work your way up. Excellent. Thank you so much for your time and your completion of this Unit 5 on chemical energetics. I will see you next time as we move on to Unit 6. Have a lovely day. See you later.